Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click the bell notification button below so that you never miss fresh videos or tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the enjoy button below for more details. My name is Sava, and today we're investigating a fundamental concept in econometrics and regression modeling, which is dummy variable regressions, which is a go-to technique to incorporate categorical variables or qualitative data more broadly into your regression analysis. Sometimes you might not only be interested in estimating the relationship between some cardinal variables, so variables that fluctuate in a scale. However, you might also want to incorporate categorical variables that basically has to do with the status of your observations, your participants, the objects of your research. And today the example that I will use to motivate dummy variable regressions is quite simple. We have got an imaginary sample of 30 students that have all taken a math exam and got the following grades out of 100, as well as it records the time those students spent to revise before the exam. What we also have here are the majors of the students, the program they study on, basically. And we've got economics students, finance students, and physics students. And we might want to know not only the relationship between the grade the students obtained during the exam and the revision time they spent, so basically how effective revision is, but also perhaps we might want to gauge some differences between students from various programs. For example, do economics students do better than finance students? Do physics students do better than economics students? Perhaps finance students are doing the best of them all. And perhaps also how categorical variables, qualitative data such as the major, where the student comes from, so basically their background, their interests, how it shapes the relationship between exam performance and revision time to start with. And obviously this is a very broad topic, and various categorical variables or qualitative data in general can be brought down to dummy variable analysis. For example, the location of companies, the status of countries. Is it an island country? Is it an ex-colony? Is it a country that belongs to the European Union? Or for survey data, what is the gender of the participant, or is the participant coming from a particular background? So the opportunities here are truly endless, and the concepts we'll learn today in this short tutorial will be generalizable to a very wide range of contexts. So to code the dummy variable, there is a very easy and efficient procedure that we can use in Excel, basically using an if function. For dummy variable analysis, it is instrumental to remember to avoid the dummy variable trap. Here we have got three categories: economics students, finance students, and physics students. And you might be tempted to just code three dummy variables for each of those majors or each of those programs. However, you need to leave one group as the reference group to prevent multicollinearity. And here we have chosen to use economics students as our reference group, meaning that all dummy variables and further estimations will be undertaken for the remaining two groups, namely physics students and finance students. And all estimations will be treating those students relative to their economics studying counterparts. Keeping that in mind, we can use the if function referring to the student status categorical variable, locking the column here as we might want to drag it across. So if it equals the value that we've got here at the top in the heading, and this means that we need to lock the row, if that is the case, our dummy variable is equal to 1 and 0 otherwise. And that's the key with dummy variables. Those are 0 and 1 variables that basically answer a question. 1 is yes and 0 is no. Does this student study physics? 1 if they do, 0 if they don't. And that can be dragged across for finance as well and down. And we can easily see that, for example, this particular student, student number 4, is a physics student, because the dummy variable codes 1 for physics, 0 for finance, obviously. And that means that this student does indeed study physics. And student 3 studies finance. That shows here 0, 1, 1 for finance. And this student, as they've got zeros for both physics and finance, study the reference group, or economics in this particular case. Again, this is something that you can easily implement for any categorical variable and generalize as follows. So first, what we might want to do is to estimate a regression model with our main dependent cardinal variable, which is revision time, controlling for the major, basically including those two dummy variables in our analysis. And there we might use the Linus function, input in the math exam grade, the exam performance as the dependent variable, as our y variable, and these three variables, revision time, the physics dummy, and the finance dummy, as the independent variables, or our x's. Then we input 1 as we do want the constant. Here, the constant would be interpreted as the expected grade an economics student would obtain if they do not revise at all. So again, quite an obvious or intuitive interpretation of the constant. And 1 for additional statistics. As we want standard errors, we want r squared for further inference, for further modeling. And we press enter to enforce this formula. And again, we need to keep in mind that Linus returns coefficients in the reverse order the original variables appeared. So here, as we've got revision time, physics, finance, he will have them in the reverse order: finance, physics, revision, as well as the constant on the far right-hand side. So here we can see that the coefficients appear in the first row. We can see that an economics student who has not revised at all is expected to get a grade of around 35 out of 100. Every hour of revision boosts the grade by 1.9 marks on average. And perhaps what we care about the most is that physics students are expected to perform on average much better, with an average grade of 11 grades higher than the economics students' counterparts, whereas finance students have got the grade in the same vicinity. To test whether those differences are statistically significant, we can calculate t-statistics, dividing the coefficients by the respective standard errors in the second row of the Linus template. And then we can test them for statistical significance using a two-tailed t-distribution, inputting the absolute value of the t-stat and the degrees of freedom that are the rightmost element in the fourth row of the Linus template. Here it's 26 because we have 30 observations, and the degrees of freedom number is reduced by 4, given that we've got 4 coefficients. Quite intuitive. We'll lock the column for the degrees of freedom, as they are the same for all 4 tests, and that allows us to see that the physics coefficient, the revision coefficient, and the constant are all statistically significant at 1%. Those p-values are less than 1%, whereas the finance coefficient is statistically insignificant with a p-value that's very high, meaning that revision indeed does matter for exam performance. That's something that we expect to see. Physics students do outperform their economics counterparts, as this particular t-statistic is positive and significant, whereas economics students do not perform particularly different to their economics counterparts. And that is quite an obvious and streamlined explanation of this hypothesis testing process. However, what might be a relevant criticism of this approach, that we include 2 variables at the same time into the hypothetical baseline model that does not have any dummy variables, and that including them individually would not make much sense, given that you either control for the major or for the program, or you don't. So what you might want to do if you are introducing dummy variables is to test whether all dummy variables that you include for a particular categorical variable are statistically significant jointly. And for that, we can use a restricted f-test, testing for joint significance or joint explanatory power over the finance and physics dummy. Because obviously, imagine that you had 50 programs, then you would have 49 dummy variables, and you could quite reasonably expect some of those dummy variables to be statistically significant just by chance, and you do not want to data mine this way with dummy variables. So testing for the joint significance of all dummy variables that you have to include is a very reasonable step to take for additional robustness. So to do that, we estimate the baseline regression, or the restricted regression, that does not include our dummy variables. That could be estimated using just the Linus function, with the exam grade as the y and the revision time as the x. Again, 1, 1 for the constant and the additional statistics. And we can see that still we have got a positive coefficient for revision that's quite similar in magnitude, and a constant that's around 40. We can quite easily apply the same statistical significance testing for the individual coefficients, showing that, well, revision is a positive and significant factor, as expected. However, how you might test the significance of those two variables jointly that we have included into our expanded or unrestricted model. To do that, we need to compare the R-squared values and see whether the R-squared of the model that has those two variables included is significantly higher than the R-squared of the restricted or baseline model. Obviously, if you include more factors into your model, the R-squared can only go up. It either stays the same or increases. So testing for the significance of that increase is instrumental. And here we have got a formula for the restricted f-test f-stat, which is quite intuitive to explain in terms of the conceptual procedure it undertakes. In the numerator of the f-stat, we have got R-squared improvement per coefficient included. So basically, we have to make sure to count by how much the R-squared has increased, divided by how many additional coefficients we have to include into the model to facilitate such an increase. And here we included two dummy variables, so this particular parameter is 2. And in the denominator, we have got the remaining variability, that is 1 minus the R-squared of the new expanded unrestricted model, divided by the residual degrees of freedom of this model. Basically, we have got the adjusted explained variability divided by the adjusted unexplained variability. Very similar to the baseline f-test, where you just test the significance of all coefficients you include into the model. And turns out you can use the f-test to assess the significance of any set of coefficients in the model if you estimate the model with and without set coefficient set. This produces an f-stat of 4.79, which can be tested for significance using the right-tailed f-distribution, f-dist-rt, inputting the f-stat first, and then as our degrees of freedom, we input first the number of new parameters, which is 2, and then the residual number of parameters in the expanded, new, unrestricted model. That returns a p-value of 1.7%, meaning that the dummy variables jointly are statistically significant at 5%. This p-value is below 5%, meaning that it was warranted to include those dummy variables into our analysis, and that this relationship is not spurious. It's not due to data mining or testing loads of dummy variables at the same time. And this procedure is more relevant if you have got more dummy variables that you have to use to explain your categorical variable. So imagine that you're testing for the difference of some effect in months of the year, and you'll have 11 dummy variables. Again, you'll use some month as a reference month, and then 11 dummy variables explaining all other months. Here, for 11 tests, you can assume that one of them will be statistically significant at 10% just by chance. So undertaking this particular procedure becomes very crucial to avoid data mining or data snooping bias. However, you might also use dummy variables even more productively in terms of informing your inference. For example, do all students revise with the same efficiency for the exam? Do, for example, finance or physics students revise more effectively for the math exam? Maybe they have got access to better facilities, or they have got better tutors. or some of their background, some of their modules they've taken, allows them to revise for math more efficiently. This can be tested quite easily using interaction terms. Interaction terms are, again, a very common concept in econometrics and regression modeling that basically takes products of independent variables and includes them as additional factors in your regression. Here we'll be able to test whether the effect of revision on performance is the same across the cohorts of students by taking the product of revision time, and we have to lock the column here as this variable is the same, and times it by the dummy variable that characterizes the student cohort. And again, here we have to leave economics as our reference group, and other two groups will be represented by those dummy variable interaction terms. And we can enforce that throughout and estimate our new model with 6 coefficients. And here we can use Linus regressing the exam grade on revision time, the dummy variables, as well as the interaction terms with revision time. And that returns a new Linus output, and we can still apply the same t-test function to assess statistical significance of individual coefficients. Here we see a completely different picture if we allow interactions. First of all, both finance students and physics students seem to spend their revision hours way more productively, with the reference coefficient for revision equal to 1.33, meaning that each economics student gets 1.33 marks more per hour spent revising, whereas the differential effects on revision effect for finance and physics students are quite a bit higher. For example, physics students get 1.28 marks more per hour revised than economics students do. And for finance students, it's even more than that. They get 1.5 marks more than economics students per hour revised. And again, calculating the total effect is quite easy. We can just sum those two up. So for example, for finance students, they would get 2.83 more marks per hour revised, and physics students would get 2.6 more marks per hour revised. And the conventional effects, which is the dummy variable effects, are much smaller. We see no difference in terms of belonging to the physics major whatsoever. So on the baseline, a completely unrevised physics student performs approximately the same as a completely unrevised economics student. And there is some negative effect for finance students. So finance students know math a little bit less than economics and physics counterparts, but this coefficient is only marginally significant. So can we really treat it as reliable? Well, that's for you to judge as an econometrician. However, here we also have to undertake the f-stat for significance testing of both of those interaction terms. Again, it would be meaningless to include them separately. We can only include both of them or none of them. So here we can also apply the restricted f-stat, restricted f-test. In the numerator, we'll have the r squared of the model with interaction terms minus the r squared of the model without interaction terms divided by 2, as we've got 2 interaction terms, divided by 1 minus the r squared of the new expanded unrestricted model divided by the residual degrees of freedom in that model. And again, it's 24 because now we have got 6 coefficients that we impose on 30 observations. That leads us to calculate an f-stat of 3.6, and we again can use a right-tailed f-distribution to assess its significance with 2 degrees of freedom and 24 degrees of freedom, returning a p-value significant at 5%, meaning that indeed finance students, physics students, and economics students have different efficiencies of revision, and the relationship between revision time and exam performance are different across student cohorts, which again leads us to assume that it's not necessarily just the varying level of math knowledge across programs, but different efficiency of revision across programs that drives the differences in exam performance between the three groups. And obviously, this is a very simple example that is motivated by something that all of us can relate to in your respective research disciplines, or for your respective interests, for like finance, economics, business. You can leverage the knowledge of dummy variables to investigate the phenomena that you care about. And that's all there is for dummy variable regressions and using dummy variables for interaction terms, as well as some tips for significance testing in Excel. Please leave a like on this video if you find it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel and consider sponsor on Patreon. Thank you very much, and stay tuned.